Hey everyone, I am Miss Hu, your physics teacher. In this video, we are going to go through Unit 6 Space Physics, which is part of the IGCSE Physics syllabus for 2023 to 2025. Now, this video is part of a series of revision videos where I'll go through every single unit in the physics syllabus, but in an overview fashion only. So don't expect to be covering everything in detail. These videos are not designed for you to learn about those topics. Rather, they're designed for students who have already learned these topics and just need a reminder about what they need to know for their upcoming examinations. That's why this is only an overview. Therefore, in these videos, we will be making a lot of references to the syllabus guide to make sure we've covered everything we need to cover. Now, so because this video doesn't go through things in detail, it's merely an overview. So if there's any particular topic that you'd like to know more about, please go and watch my video on that particular topic that will go through it in more detail so that you can improve your understanding on that particular concept. So let's get started. So first things first, you need to know about the Earth. You need to know that Earth is a planet and it makes a rotation around its axis once approximately 24 hours. That means one full rotation is 24 hours, and you need to know how to use this knowledge of its rotation to explain how the Earth is able to get the periodic cycle of day and night. Now, this is actually primary school science. So by now, you should already know this as well as how to explain it. Why this is coming out in IGCSE Physics? Because we just got to make sure at year 11 you are aware about this basic information about the Earth. In addition to knowing about its rotation, you also need to know that the Earth is tilted. That means the axis is not straight, but rather it is tilted, and the angle of the tilt is approximately 23.5 degrees. This tilt is what explains why we get the different seasons in different parts of the world. Something you need to know as written here in number 2. So you do need to know that the Earth orbits around the Sun, and the time for one complete orbit of the Earth around the Sun, which is known as 1 year, is approximately 365 days, or to be more specific, 365 and a quarter days. So this is why we get a leap year every 4 years, because these quarter days all accumulate, and after 4 years we get one full day. So every 4 years, one leap year with an additional one leap day. So every 4 years you get a leap year which has 366 days. The combination of the tilt of the Earth together with the Earth's orbit around the Sun is what gives the different countries on the Earth the nature of seasons. So you'll find that there are some countries, both in the northern and southern hemisphere, that get 4 seasons. You get the spring, summer, autumn, and winter. There are also some parts of the Earth where they don't get all these 4 seasons. For example, the countries that are closer to the equator that just have hot weather throughout the year. And then there are some parts of the Earth where in different times of the year they have 24-hour sun or 24-hour darkness. You need to know that this is all because of the tilt of the Earth and the orbit of the Earth around the Sun. You also need to know that the Moon takes about 1 month to orbit the Earth, and 1 month is approximately 28 days. So you need to know about the moon cycle of phases, which starts with the new moon, then you've got the waxing crescent, the half moon, waxing gibbous, full moon, waning gibbous, another waning half moon, and then the waning crescent back to new moon. So we're not going to go through the moon cycle right now in detail, just reminding you that this is what you need to know. In addition, you need to know how to calculate the average orbital speed, which is basically the speed of the object that is making the orbit. So you need to memorize a formula as given over here. And the formula is actually very logical. V is the orbital speed, and speed is distance over time, right? So the one on top here is the distance. So 2 pi r is the formula for the circumference of a circle. So the distance covered by the orbiting object is the circumference of that circle. However, as you should know by now, the orbit is actually not circular. It's actually an ellipse shape. So that's why r is the average radius, because the value of the radius is not fixed. You can see that the radius is changing as the orbiting object moves along that path. So r is the average value of the overall radius of the entire ellipse. So that's why r, average radius. T is the time. So in this case, T is the time taken to make one complete orbit, also known as the orbital period. So when you look at the formula, very logical. Orbital speed is equals to the distance traveled, which is the circumference of the orbit, divided by the time taken to make one complete orbit. This equation applies not only to Earth, but to any planet that's orbiting the Sun, as well as the Moon that's orbiting that planet. Let's move on. Next, you need to know about the solar system. So as you can see in this list, you just need to be aware that the solar system contains the following. It contains one star, which is the Sun. You need to know the 8 planets, their names, and their order from the Sun. Okay, so specifically, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. You need to know that the solar system contains minor planets, such as the dwarf planets, including Pluto, and the asteroids in the asteroid belt. You need to know the solar system contains moons, which orbit the planets, and also the solar system has other smaller bodies, such as comets and natural satellites. So when you look at this list, you only need to know that these celestial bodies exist in the solar system. You don't need to know how many moons there are around the planets. You don't need to know the names of the moons or the names of the comets, the names of the dwarf planets, except for Pluto. The only objects you need to know the names of are the 8 planets that are in the solar system. So just be aware, the solar system contains all of this. There's not much else you need to explain, actually. Having said that, though, what else you need to know? Well, you need to know that in comparison to each other, the 4 planets nearest the Sun are rocky and small, while the 4 furthest are gaseous and large. Let's just backtrack a little bit. So the 4 planets closest to the Sun, Mercury, Venus, Earth, and Mars, are all rocky and small. And this should be very logical because of their proximity to the Sun. So when they're closer to the Sun, they're a lot hotter, which means that elements with low boiling points will exist in gaseous state. So the only things that can exist in solid state are materials with very high melting points. So things like, well, metals and rocks. So that's why the core of these 4 planets are rocky. And because rock has high density, that's why they're a lot smaller. The 4 planets that are further away, however, tend to be larger and gaseous because they're further, so they're not so hot, much cooler. That's why elements with low boiling points can now exist in solid state. And because their densities are so much lower, they are able to exist with a larger volume. That's why we call them gas giants. So they're larger and gaseous. And we call them gaseous not because they exist in gas form, but rather because what we know as gas, that's solid to them. Now, you also need to be aware of the accretion model. And a reminder, the term accretion here means the formation of an object due to accumulation of materials. So the theory is that the celestial bodies in the solar system are formed through the accretion model. So from the Big Bang, there's a lot of dust and gas, and these dust and gases start to form layers that eventually become the different celestial bodies like the planets, the asteroids, the comets, and even the stars. So in the solar system, we picture it as all the dust and gases start to accrete. That means they start to form layers, and the different formations here will start to form different celestial bodies. So we get different planets, we even get the sun, and all of these start to form the solar system with the individual bodies, the sun, the 8 planets, comets, dwarf planets, all those different bodies that exist in the solar system. Now, in addition, you also need to know the relationship of the strength of the gravitational field. So for one, you need to know that the strength of the gravitational field on the surface of a planet depends on the mass of the planet. You have to be aware that when the mass of the planet is higher, the gravitational, which I'm just going to write G here, is a lot higher. So planets with greater masses have greater gravitational field strength. Secondly, you also need to know that when the distance from the surface of the planet increases, the gravitational field strength decreases, which should make sense because the further you are away from the planet, then the weaker the gravitational pull is. So you just need to know these relationships. You also need to know how to calculate the time it takes for light to travel a significant distance between objects in the solar system. So for this, it's very simple. You just need to use the speed formula, which I'll write over here. So the speed, which I'll write here as v, is quite simply distance over time. So the time, of course, is t, d is a distance, v is the speed of light, which you should know is a constant value of 3 times 10 power of 8 meters per second. So to calculate the time it takes, it's just a matter of using the speed formula, distance over time. Now you also need to know that the sun contains most of the mass of the solar system. So similar to number 3, right? Although the sun is not a planet, but because the sun contains most of the mass, greater gravitational field strength. So because the sun is the body that contains the greatest mass in the solar system, that's why all the planets orbit the sun, because the sun has the greatest gravitational field strength. And this strong gravitational field strength is what keeps the objects in orbit around the sun. What else do you need to know about the solar system? Well, you need to be able to analyze and interpret planetary data about orbital distance, orbital duration, density, surface temperature, and uniform gravitational field strength at the planet's surface. So what we have here on this slide is an example of a table of information about the data of the different planets. Do you need to memorize this information? Good news, no. Normally, what they'll provide to you in the exam question is a table with some selected information. What they want to test you on is how to analyze and interpret the data. So by observing the information, you've got to be able to come up with an interpretation and a conclusion to answer the questions in the examination. So it depends on what the question is asking. For example, they could ask you to relate the distance of the planet from the sun with the orbit time of the planet around the sun. So you don't have to memorize it, just look at the data, look at the relationship, come up with a correlation, and then provide the answer to the question that they've asked. So this is actually testing your analysis skills. So let's move on. What else you need to know about the solar system? So as mentioned earlier, you need to be aware that the orbits are not circular. So planets, minor planets, and comets all have elliptical orbits. The thing is that you must understand is that the sun is not at the center of the orbit. Rather, it's at one of the focus points. So we've got the orbit. There are actually 2 focal points. We're not learning about ellipse in great detail. That's more of a mathematical concept. For now, just be aware that the orbits are an ellipse. There are 2 focal points in the ellipse, and the sun is at one of the focal points, not at the center. You also need to know that the strength of the sun's gravitational field decreases and the orbital speeds decrease as the distance from the sun increases. That means that when the planets are orbiting the sun, the closer they are to the sun, the stronger the sun's gravitational field on it. It makes sense, right? Because the sun has gravity. So the closer the planet is to the sun, the stronger its gravitational field strength. And the further away, of course, the weaker. And the speed of the planet also changes. It's not a constant speed as the planet orbits the sun. Because the sun's gravitational pull is stronger when the planet is closer, it will make the object move faster because stronger gravity. The further away, weaker gravity, so weaker pull, therefore the speed is also slower. And based on that, you need to know that the object in the elliptical orbit, it travels faster when it's closer to the sun and slower when it's further away from the sun. So you got to use the conservation of energy to explain this. So how do we use it? Remember that motion energy is kinetic energy. So here it's faster. Hence, when it's faster, there's greater kinetic energy. I'm going to write that here, kinetic energy. So it's similar to the concept of conservation energy, which you have learned in Unit 1. There is a transfer of energy. In this case, from kinetic energy here, it is then converted to potential energy, which let me put a different color here. So at this end here, it's more potential energy. So there is a constant conversion from potential energy to kinetic energy. So when it's faster here, more kinetic energy. Then as it moves away, it slows down, it is converted to potential energy before becoming kinetic energy again. So you have to know how to explain this change in the energy and the speed using the concept of conservation of energy this way. Next, you need to know about the sun. The sun is a star of medium size and it contains mostly hydrogen and helium. The reason why it contains mostly hydrogen and helium is because hydrogen is the most basic element that exists in the universe, and this hydrogen element is formed during the Big Bang. Nuclear fusion reaction, as you can see, number 2, is what powers the stars. So our sun, which is a star, undergoes nuclear fusion reaction, which fuses hydrogen into helium. And that's why the sun is made up mostly of hydrogen and helium. This nuclear fusion reaction is what produces the energy of the sun. And as you can see, number 1, most of the energy is radiated in the form of infrared, visible, and ultraviolet regions in the electromagnetic spectrum. Next, you need to know about stars. So in number 1, you need to state the following. And when we say state, it means you just need to be aware that this exists. Do you need to be able to explain them? Not so much, just state. So you need to state that the galaxies are each made up of many billions of stars. The sun is a star in the galaxy known as the Milky Way. So we are all residing in the Milky Way. Now, the other stars that are part of the Milky Way are much further away from the Earth than the sun is from the Earth. So very, very, very far away. And astronomical distances are measured in light years, where 1 light year is the distance traveled in the vacuum of space by light in 1 year. Remember that the term light year may sound like time, it's actually distance. How far light travels in 1 year? This year that they're referring to, of course, is 1 Earth year because that's what 1 year is to us. Now, do you need to know the value of 1 light year? Yes, you do. As you can see in number 2, you need to know that 1 light year is equal to 9.5 times 10 to the power of 15 meters. So I'm just going to highlight that because you need to know it. But what if you can't remember it? Now, actually, you don't need to memorize it because if on the chance that you're required to recall this value, you can actually work it out. By now, you should already know that the speed of light in vacuum is 3 times 10 to the power of 8 meters per second. So I'm going to write that down. From this, you can actually calculate the value of 1 light year. We know that 1 light year is the distance traveled by light in 1 Earth year. Using the formula of speed equals distance over time, so I'm just going to write that here. You can calculate the distance as speed times time. So if you want to calculate the distance, you just need to take the speed of light which is 3 times 10 to the power of 8, and multiply it with the value of 1 year in seconds. So how do we get that? So we know that there are 24 hours in one day. 1 hour has 60 minutes. I'm going to bring that to the next slide. 1 minute has 60 seconds. And then you need to multiply this with 365 days. What you will get if you use your calculator is you'll get a value of about 9.46 times 10 to the power of 15. Or you can write this as 9.5 because, as you should know by now, IGCSE, we prefer to write the values to two significant figures. So that's how we get 9.5 times 10 to the power of 15 meters. So you got to remember to convert the time to seconds. And why seconds? Because the unit for speed is meters per second. So you have to get the time in seconds, and then when you multiply the speed with time, you'll get the value of the light years in meters. So yes, you do need to know the value of 1 light year. If you can't memorize it, then just work it out using this method. Now, you also need to know the life cycle of a star. So I'm just going to go to the next slide because we've got the chart over here. So we need to be able to describe the life cycle of a star. You just need to be able to describe what happens. You don't really have to explain. So what you need to be able to describe? You need to be able to describe that a star is formed from interstellar clouds of gas and dust. The interstellar clouds of gas and dust is known as a nebula, right? So a nebula basically is these clouds of gas and dust, because when the Big Bang happened, lots of gas and dust are floating around. They start to form clouds. Those clouds are known as nebula. And within this nebula, the protostar starts to form, as you can see in this chart. The protostar is basically the interstellar cloud that's collapsing and increasing in temperature, because what happens is these gas and dust start to get together, they pull in together, and they start to form through the accretion model, right? They start to get stuck together. And because of its increasing mass, it starts to increase in terms of its gravitational acceleration. And then the protostar eventually becomes a stable star. Now, in this diagram, which I have taken from the internet, it includes a T-Tauri phase. You don't actually need to know the T-Tauri phase. So we're going to skip that. You just need to know from protostar, it becomes a stable star. So here the stable star is quite simply the main sequence. So the protostar becomes a stable star when the inward force of gravitational acceleration, because of its high mass, is balanced by the outward force due to the high temperature in the center of the star. So in the sun, there's the nuclear fusion reactions that's producing energy. When this inward force is balanced by the outward force, it's stable. But logically, as you should know, eventually the fuel runs out. So when the stars eventually run out of hydrogen, then there's no more fuel for the nuclear reaction. The outward force starts to decrease. So what happens is the inward force starts becoming greater than the outward force. So you can see from this chart here, this is when the stars are stable, and when the forces start becoming unbalanced, that's approaching the end of the life cycle, so it's going into old age. Now, whichever path that they take depends on the mass of the stars. So for low and medium mass stars, they will start to form red giants, whereas the more massive ones form red supergiants. So what are red giants and red supergiants? So this is when most of the hydrogen in the center of the star has already been converted to helium. That means the nuclear fusion reactions have happened, it's running out of hydrogen, so there's very little hydrogen left. Most of them have already been converted into helium. So if we look at what happens to the low and medium mass stars, they will form a planetary nebula with a white dwarf at the center before forming a black dwarf. The red supergiant, on the other hand, will explode as a supernova, forming a nebula containing hydrogen and new heavy elements. The remnant of the supernova could either produce a neutron star or a black hole. And the nebula from a supernova could possibly form new stars with orbiting planets. Next, let's move on to the universe. So what you need to know about the universe, you need to know that the Milky Way is one of many billions of galaxies making up the universe, and the diameter is approximately 100,000 light years across. You need to know about redshift. So redshift is an increase in the observed wavelength of the electromagnetic radiation from receding stars and galaxies. So receding means to move away. And the light emitted from the distant galaxies appear to be redshifted in comparison with the light emitted on the Earth. And this redshift is evidence that the universe is expanding, and this supports the Big Bang theory. If we look at this comic, which is a very famous comic, in fact, it's very like high-level thinking. So what this comic is depicting is light from an object moving towards us will appear blue shifted, whereas the light from an object that's moving away from us appears to be red shifted. Now, in addition to red shifting, you also need to know about cosmic microwave background radiation, or CMBR for short. You need to know that the CMBR was produced shortly after the universe was formed. It means after the Big Bang. And initially, the radiation is actually very short in terms of its wavelength, but slowly has been expanding as the time has passed, and now it has expanded into the microwave region, which is why it's known as a cosmic microwave background radiation. You need to know that the speed at which the galaxy is moving away from Earth can be found from the change in wavelength of the galaxy's starlight due to redshift, and the distance of the far galaxy can be determined using the brightness of a supernova in that galaxy. Let's going to move on to the next slide, from which we can just take a quick look at the concept of redshifting and CMBR. So here at the bottom, this is the reference for our light spectrum. So from a star that's far away from us, you can see that the spectrum has kind of shifted very slightly towards the red. A nearby galaxy, which is even further away, the spectrum has shifted even more. Distant galaxy, even more. Very distant galaxy, even more so. So you can see that the further away the stars or galaxies are from us, the more red shifted the light spectrum is. That means that the light spectrum has shifted closer towards the red end of the spectrum. In terms of CMBR, this is just a universe map of the CMBR. You don't actually need to know this map. I've just put this picture here just because. So this is what you need to know about redshifting and CMBR. You also need to know about the Hubble constant. The Hubble constant is the ratio of the speed at which the galaxy is moving away from Earth to its distance from the Earth. And this can be taken from the formula given here, which is h naught equals v over d, where h naught is the Hubble constant, v is the speed at which the galaxy is moving away from us, and d is the distance of that galaxy from Earth. You must also know the current estimate for the Hubble constant, which is about 2.2 times 10 power negative 18 per second. And that if you want to calculate the age of the universe, you can use the inverse of the Hubble constant, which is 1 over h naught, and that will provide the estimated age of the universe. So this diagram is just actually showing us how the light can be redshifted, and this is a graph that shows the relationship between the distance of the galaxy from Earth and its velocity. So the greater the distance of the galaxy is from Earth, we find that the speed at which that galaxy is moving away from us is also much greater. The gradient of this line is the Hubble's constant. So if we want to calculate the age of the universe from the graph, it is basically the inverse of the Hubble constant or the inverse of the gradient of this graph. And that's pretty much it for this unit. So if you found this video to be educational and helpful in your preparations for your examinations, please click like and subscribe for more physics lessons from your physics teacher, Miss Ho. Happy studying and all the best for your examinations.